Hi guys, good morning. How are you? Good morning to your destinies. It's another day, another beautiful day, guys. Like I promised you, I will be showing you, I'll be taking you through the topic of spring, that is strength of materials. Please follow my YouTube channel and watch more of these videos. Today I want us to look at 2022. This is strength of materials and mechanics of machines, October-November series 2022. So you have diploma in mechanical engineering, production option, plant option, diploma in automotive engineering, diploma in welding and fabrication, and diploma in construction plant engineering, module 2, strength of materials and machines. And this paper is very easy. Now I'm dealing only with strength of materials at the moment. Yet later, much later, I will help you through also mechanics of machines. I will show you how to derive equations with torque, questions with clutch, questions on the topic of clutch, topic of flat belts, topic of moment of inertia, momentum, and all those. But today I want us to look at strength of materials, and the focus topic is springs. I've told you spring is a very common question. It usually comes most of the times as an independent question. That it means it has 20 marks by itself. So if you can get the 20 marks by themselves in an exam scenario and also do question to do with shafts and torsion, 20 marks, you've already passed this exam. You even don't need to do the part B, but because the examiners requires to see how much you've been taught, you will have to do part B as well. But if you do well in your part A and part B, you do a little bit well, then it means that you have already passed your exam. So let us look at this question. It says, question number 4, with the aid of sketches, distinguish between closed and open coil spring. Distinguish between open and closed coil spring. So for open coil spring, these are helical springs which are heavily used in automotive, especially when designing McPherson's strut unit. That is a suspension that is heavily used with Isuzu D-Max, double cab and single cab. It's a suspension system that is heavily used by other vehicles. So this is now the closed coil. There is no gap in between them. So this is there from here to here. This distance from here to here, this is the diameter. That is the wire diameter. Then from this point to this other point, we have the radius of the coil, or D over 2, diameter divided by 2. Then from here to here, that's where we have the length of the entire coil. And then we have the load being applied in this part. This is W, axial load. That is now closed coil spring. And then we also have open coil helical spring. Open coil helical spring, it has a helical, looks like this. This one has a helical angle. This one has a helical angle. That's how it looks like that. This is the helical angle phi. So from this part to this part is what we call the pitch. This is the pitch. Then we have the coil diameter as well. That is capital R, and this is the W load. So by doing so, you already have the 4 marks. You've distinguished with the need of a sketch. So distinguishing them, you will only say, you can add a small message here and say, with open coil helical spring, there is the provision of an helical angle into brackets phi. But with the closed coil, there is no spaces in between the turns. then you get your 4 marks like that. That's how you get your 4 marks. So go to part B. Part B of the question. Part B of the question is saying that a semi-elliptic leaf spring carries a central load W. Show that the maximum bending stress that is in the spring is given by 3 times load times length over 2n bt square. That is where we are told that L, show that this is equals to length W 3 all over 2 times number of turns times T times 12, where we know that W is the load, L is the length of the spring. So the first concept is that you grasp, is it a quarter elliptic spring or a semi? If it's a semi, you know how to derive. Then we have B is the breadth. Then we have N is equals to number of turns, number of plates. Then you have T is equals to the thickness of each plate. So what you do, you must first know how to draw. In the previous video I've shown you how to draw the semi-elliptic and the quarter elliptic. Suppose it's simply supported from both ends. That's how it looks like. That's how it's simply supported. Then the load here is acting like that. So the load acting here, it is W divided by 2, and the other load acting on this other end is W divided by 2. So the distance from here to here, the length, this is now the length of the spring. That's what they're saying. This is the side view. This is the front view. The side view of the spring will be like this. It will be a section like that. It looks like this, where we have the breadth and this is the thickness. We have B and T, breadth and thickness, like that. That's how it looks from the side view. So we have the B and the T. Then the number of from here to here, that's when we have the number of, we have N, we have the number of plates. So I've shown you everything. We have shown you the W, the L, the B and the T and the N in my drawings. So the next thing now, it is to derive. So from this instance, you know that the bending moment, that taking your moment from the middle of the spring like this, the distance from here to here, it will be L divided by 2, and the distance from here to here will be L divided by 2. So you take the moment from the middle, that is the moment, that is the twisting moment, that is M. From this point, this is M. You take M from there. That will be the distance. And we know that moment from module 1, moment is equals to force times distance. So the force acting from the middle, it is W. The force acting not from the middle, the force acting from one edge of the, or from one section of the edge is W over 2 times the length is the length from now here to this side, from this side to this side. That is the force. The moment, the clockwise moment and the anti-clockwise moment acting, particularly here, it is W2 over L divided by 2. So the total moment is WL divided by 4. And for number of plates, it will be, for n number of plates, it will be L over 4 times 1 over n times 4n. That is now for the number of plates, or for one leaf, which is 1, which is the answer is 1. Again, having known that, that is the first moment. Now, that is the bending moment. We also know that the relationship between the moment, a moment, and area of inertia is equals to shear stress over y. And from this moment, we know to make shear stress subject of the formula, it will be M times Y all over I. So we know that M is equals to load times distance over 4n. So substitute into, let's call this equation 1, into 1 it will be, I mean, substitute it to equation 2, not equation 1. This is equation 2. Equation 2, it will be shear stress is equals to WL over 4N times Y times 1 over I. We know that area moment of inertia of a circular section, it is pi d raised to power 4 all over 64. And you know that Y is equals to T divided by 2. So you substitute all these again, substitute into 3, substitute into 3, you get that the shear stress is equals to WL over 4 and times T, that is T over 2, again times the reciprocal 64 over pi d raised to power 4. That is pi d raised to power 4. That is how you find the you derive the equation. Sorry, there's somewhere, this is not a circular section. The I for a circular section is this, but this one is not a circular section. This one is triangular, is a rectangular section. So for a rectangular question, the moment of inertia is bt raised to power 3 all over 12. So correct this. This is not a circular section, this is not torsion. This is a rectangular section, so it will be 12 all over bt raised to power 3. Then now you simplify. So simplify. 1 will go here 6 times. Then 4 divides by the other 4. So it is WL by 2 by 2 3. Then T1, it will be T raised to power 2. This section, there is nothing else. It will be now 3WL all over 2N BT raised to power 2. Hence proved. So by now you've gotten the 10 marks. You've distinguished. Then now you have practically derived the equation which you are told. The concept here is to know the moment from a section of the leaf, then the relationship between the moment of the moment and the area of inertia. You divide it by y, by shear stress over y, and that's how you get your answer like that. So let us look now at part C, which is also very simple. Part C of the question. The part C of the question asks you, a semi-elliptic leaf spring is to be designed to carry a load of 6 kilonewtons. So analyze the data given. Analyze the data given. So at this section we have 6 times 10 raised to power 3 newtons. That is your W. The stress of the spring is not to exceed. So you have been given the stress is not to exceed 142 times 10 raised to power 6 newtons per meter squared. Then, and the length is to be 440 millimeters. So length in meters, it should be 0.54 meters. That is the length. And then you're told the thickness and the breadth of the available plates, that is T, the thickness is 0.008 and breadth is equals to 0.09. 0.09, that is 90 divided by 1000. Yes, it is 0.09 meters. All these dimensions are done in meters. Then the modulus of rigidity. The modulus of rigidity, that is E, is equals to 210 times 10 raised to power 9 newtons per meters squared. So we are told first part of the question, determine the number of plates required. Number of plates required. So to determine the number of plates required, we know very well, as we have seen in our first equation, that shear is equals to, as you have derived, 3WL all over 2NBT raised to power 2. So this is so simple. So shear, you've been given shear is 142 times 10 raised to power 6 is equals to 3 times 6 times 10 raised to power 3 times the length, which is 0.54, all over 2 times n times b, which has been given as 0.09, times t, 0.008. Then this is t squared times n. So making n subject of the formula, it is 3 times 6 times 10 raised to power 3 times 0.54 all over 2 times 0.09 times 0.008 squared times 142 times 10 raised to power 6, like that. Again, so we now punch it. Now punch, you say 3 times 6 10 raised to power 6, 6 raised to power 6 raised to power 3, like that, 6 raised to power 3, like that, times 0.54. What is your answer? Your answer is 9720. You divide it by what is 2 times 0.09 times into bracket 0.008 raised to power 2, close the brackets, like that, times 142 times 10 raised to power 6, like that. It is 1635.84. So our n is equals to 9720. You divide by the answer. Our n is 5.9419, where we cannot have the number of plates being in decimals, so you round off. Our n is equals to 6 plates. So you have already answered the first part of the question. So these were 20 marks. These are like free marks, guys. These are free marks. Follow keenly. Then you have part 2 of the question. Again, you're told the radius of the plate should be the radius of the plates should be formed. That is the radius. What is the radius of the plate? And now the radius is the same as close to the deflection. You know, the radius is inversely proportional to the deflection of the spring. So the first thing you do, you will draw. You first assume it is a circle. It is circular because the springs are always curved. So we assume them to be in a circular manner. Then you draw your spring. That is your spring. Your springs looks like this. That's how they look like. So having done this, the radius of this circle, you can take it from this point, and the other radius of the circle, you can take it from that point. Then you can take the length of the leaf from that point, like that. Then you can maybe section it at this middle. So here we have the radius, and here we have the radius. And then from this part, which is in the middle, we have length divided by 2, length divided by 2, because the entire length of this is one length. It is length. So length divided by 2, like this. So the deflection, that is now from this part, how it has deflected. This is a deflection from this part to this part. That's what we call the deflection. From this part to this other part. That's what we call the deflection. So the distance inside here, it will be r divided by deflection. The distance. So as I was telling you, so from this point here up to this point where this circle ends, this is where the deflection is. As you can see, this is where it has deflected. It has curved. So this is deflection. So we also know that from here to here, it is r. So the distance from here to here, this inside here, it is r minus deflection. So having done that, you will now apply where I've told you that, let's say this is A, this is B, this is O, this is C, and this inner part here is D, like that. So this is where the D is. This is A, this is B, this is C, this is O. So here we will employ the concept of Pythagoras theorem. There will be some little mathematics. R is equal to the radius of curvature. R is equal to the radius of curvature, and R is equal to OC, which is equal to OA, which is equal to OB. If you go back here, R is equal to OA, which is equal to OB, which is equal to OC. This is the C. This is where C is supposed to be at this point. OC, like this. You get? Then we know that BC as well. BC is equals to what? Deflection, which is equals to deflection. That is DC, it is deflection. That is from here, this is from here to here, from here to here. That's what we call DC. That is what we call deflection. Then we have OD. OD is the same as OC, which is the same as DC, which is the same as R minus deflection. That is OD is the same as OC, which is also the same as DC, which is the same as DC, which is the same as R minus deflection. I've told you how we have found this. So using Pythagoras theorem, you know, this is a right angle triangle like this. It looks like that. So from here, let's say now this is O, this is D, then this is B. From this concept, we know very well to find OB squared. OB squared is the same as saying OD squared plus BD squared, like that. That is the same as saying OB is the same as R squared, the same as OD is the same as R minus theta. That is R minus theta, which is squared, plus the distance between OD, the distance between BD, that is BD. BD is the same as L over 2, as you have seen, squared. So opening the brackets, R minus deflection, R minus deflection, open the brackets, this is module 1, pure mathematics. Open this is R squared minus R deflection minus deflection R plus deflection squared. That is negative times negative to be positive. Now, this one, as it's approaching 0, it is very small. That is, delta squared is very small, very small. So we assume that it is gone. So we are remaining with R squared is minus 2R theta, because this and this are like terms. By using Pythagoras theorem, plus L over 2 squared is the same as R squared, like that. So when you open the brackets here, it will be R squared minus, you bring this on the other side, bring this R on the other side, it is minus R squared is equals to, this one take it on the other side, to R deflection minus L squared over 4, like that. That's how it looks like. So this one will also cancel out, and that will be 0 is equals to 2R theta is minus L squared over 4. So take this on the other side, it will be L squared over 4 is equals to 2R R delta. When you get that it is equals to R delta, you now make R subject of the formula. That is, make R subject of the formula. So it will be L squared over 8. L squared over 8R is equals to deflection, or R is equals to what? L squared over 8 delta, like that. So we are told to find the radius of the curvature. That is this R. This is what the question is asking, right? The radius which should be formed after the cavitation. So the radius which should be formed is R, this R. So R is equals to L squared, we have been given as 0.54 squared all over 8 times deflection, times the deflection, which we do not know, which are not given in the question. So it means we must also find the deflection, which is not difficult. I must find the deflection. So guys, so we have been told, in the question we have been told to find R, and we have seen we have been stuck at this point because we don't know the deflection. We have the other values, but we do not have the deflection. So to derive we have to derive the deflection. Deriving the deflection is very simple. So deriving the deflection, you equate between the moment over area of inertia is equals to modulus of rigidity over the radius, like that. Having used this, we know that the moment of this semi-elliptic leaf spring, as we had derived it, is W times L over 4N. And we also know that the area of moment of inertia of a triangular section is B. It is BT raised to power 3 all over 12. So we substitute this into this formula. That is WL over 4N times reciprocal of this is 12 BT raised to power 3 is equals to the R which we have just derived here. Sorry, we also have R. R we have said it is equals to, I've said that R is equals to L squared all over 8 and the deflection, that is delta. So is equals to E times reciprocal of this is 8 delta all over L squared. That is ER. That is R. You find the reciprocal of it. So you make this, you want to make this delta subject of the formula. So here 1, here 3. That is 3 WL all over BT raised to power 3N is equals to E 8 all over L squared. So delta equals to, making delta subject of the formula, is 3WL raised to power 3, that is L squared times L times W times 3 all over E N BT raised to power 3. That is now the equation. That is how you find the equation. Then there is this 8 here, so you put your 8 here, this 8 here. So it is 8 E N BT raised to power 3. That's how you find your deflection. So in our question, you've been given the data. As we analyze the data that we were given all these values. So we find the deflection. So deflection is equals to 3 times the load. The load on the load in our question was 6 times 10 raised to power 3 times L raised to power 3, that is 0.54 raised to power 3 all over 8 times E. Our E you've been given as 210 times 10 raised to power 9 times N, which you have just found to be 6 plates. We've just found 6 plates with our N times 6 times B. Our B we are given as 0.09 times 0.008, that is our thickness, raised to power 3. Then what is remaining is to punch. What is remaining is to punch. So it is 3 times 6 times 10 raised to power 3 times 0.54 raised to power 3. That is the length, 0.54 raised to power 3. So our answer is 2834.352 all over 8 times 210 times 10 times 10 raised to power 9 is like that, times 6 times 0.09 times 0.008 raised to power 3, like that, 8.003 raised to power 3, like that. So that is 486.4. So you say 2834.352, divide the answer. You find that our maximum deflection should be 0.006102 meters. That is the maximum deflection. So having this, we say that R is equals to L squared, as we have derived 8 theta. So that is 0.54 raised to power 2 all over 8 times 0.006102 squared. No, 0.02 as it is. So the answer we have here times 8, you get that. Then you say 0.54 raised to power 2, close the brackets, divide the answer. 0.54 raised to power 2, divide the answer. You get that our radius of curvature, it should be 5.9733 meters. So guys, you have checked, I've told you everything. That is the radius of curvature. No, this should be in millimeters. That is the radius of curvature, as I've told you. Guys, please subscribe to this YouTube channel. I will show you that's how you take 20 marks home. As you have seen, I have done in all those videos, I have done all these questions. I've done the 2016 question, and I've also given you the other part of the question, that is 2022 past paper question. There is nothing that I've not done for you guys. Please subscribe to this YouTube channel, and next time now I will teach you torsion. I'll touch on torsion, and I'll also touch on mechanics of machines. I will touch on flatbeds and clutches. the Lord bless you.